Hi, welcome. Thank you for coming for my talk. Today I will tell you about a project we, Meme Solutions, did together with GIVT about predicting flight compensation. And I will tell you things that can happen when trying to implement such a machine learning project. So what is GIVT? Is a company that helps passengers to get compensation for disrupted flights. The main reason for this compensation is EU 261 directive. It's a law that lets passengers get compensation for flights that are delayed for more than 3 hours, or cancelled, or maybe denied boarding, things like this. And the way the company works is that when a client comes to a company and says, well, my flight was delayed 4 hours, can you help me get the money? First, the claim is verified. So whether this case is actually eligible for compensation. Then the company sends the claim to the airline, and then airline can accept the claim and pay the money, or reject the claim, and then if the claim is rejected, you can go to the court, which is long and tedious process, so no one wants to do it. Well, but hopefully, eventually, it ends up in client getting the money, and the company gets a cut of this compensation, if it's successful. And to tell you about the size of this market, so there are 4 billion passengers annually. 1 billion of those passengers comes from European Union. And making some estimates about how many flights are actually disrupted, you end up with that there is 5 billion of euros available for, should be paid in compensation to passengers every year. This number is not realized because many people don't know about this, and sometimes the airlines reject the claims. But this is the scale, the potential scale of the market. So when can passenger get a compensation? So there are basically 3 situations: when there is a delay, more than 3 hours; when the flight is cancelled and you do not get a alternative flight within 2-hour window; or where there is overbooking and you're denied the boarding to the plane. But it's not so simple. So you cannot get compensation when the delay is less than 3 hours, when you get the alternative flight. But there are also other conditions, like the asterisk on the compensation, which can be summarized as the extreme weather, a strike, so on the airport, say, or some other rare events like lightning hits the plane or a plane hits a bird on its way. Then these are unforeseeable circumstances, and then the airline is not obliged to pay you. And the problem we want to solve is to automate the verification of claims. So a client comes with a claim, and we want to answer the question, so should we take this case? Should we say to the client, yes, you are entitled to the compensation? And the standard approach in a machine learning project is to first collect the data, train the model, deploy the model, and then hopefully profit from this. So the perfect model, the simple, the way you would love to solve it, looks like this. First, you check if the flight is eligible, because this EU 261 directive is applicable only to airlines that originate in the European Union, and to flights that originate from EU. So not all flights can be compensated. Then if yes, then is the delay greater than 3 hours or the flight is cancelled? Well, if yes, then, so was there some extreme event like weather strike, bird hit, this sort of thing? Well, if no, then you're entitled to compensation. And it looks very easy if you have the perfect data, but you often don't have perfect data, and there are complications in this third decision point. So maybe there was a strike, but it wasn't strike on the airport, but the airline was on strike. The employees of airline decided to go on strike. Then you still are entitled to compensation. Basically, if the delay or cancellation is the airline's fault, and the strike of airline crew is understood as airline's fault, then you're entitled to compensation. But if it's not airline's fault and the airline could not foresee it, you don't get the money. So another case is maybe the strike was on the previous airport. So the plane, so it goes from one airport to another, then another, then another, then another. And there, if there is a strike on some airport previously on the path of the plane, then this still counts the airport strike, say. Then this still counts as unforeseeable circumstance. So you can already see that this third choice, this extreme bad weather or strike question, this is not so easy. And for this, we need machine learning. So to solve the problem, we need to collect the data. Right, so we need flight information. This, so information about what was the actual takeoff time, right? When the flight took, when the plane took off. The second thing we need, when it landed actually. So was it on schedule or was it late? Well, we need to know the airports. We need to know other data of this type. And this data of this type can be bought. You simply need to, it's very hard to collect it yourself, but there are providers that collect this type of data, and you just buy this information. This is not always perfect because depending on the provider, you sometimes get the data with a 2-day delay, or sometimes there is some missing data, some flights are missing, some data about flights are missing. The other type of data that we need is information about weather. And this we get from something called Matter weather reports. They are issued every 30 minutes for every airport, and then contain information useful for the flights, so like visibility, wind strength, wind direction, etc., etc. And you can get them for free. There is a US agency that provides this data. But the data is still not perfect. So example of something that happened a few days ago, so like 2 days ago, the system extracted the weather report that you can see on this picture. This long string at the bottom, this is how the report looks like. But there is also something that is supposed to be the hour of the report. And there is 80 there. And what can I do with this? So what time was the report generated? I know that we queried the service at around 8 a.m., so this is probably 8 a.m., but sometimes this data is missing completely. So there are problems with the data, and there are the other things, like strikes, hitting birds, and this is hard. This is hard mainly because this hitting a bird affects the next flights of the plane. So if a plane hits a bird on its way, then it needs to be checked for damage, and then this delays the next flights. And we tried extracting this information from Twitter accounts that tweet about aviation, and it didn't work because it didn't really match well with the data we have. Okay, so we have this data that is not perfect. So we collected the data, but there were a lot of things missing. So of course you can say change the provider of the data, right? This is the basic thing. If your provider's data has 20% of flights missing, then well you maybe need to change it. So we tried that. You could manually fill missing values. So the process that happens in the company is instead of a human verifying the flight, as when there is missing data. So you get a case, and then the case has no arrival time. And so you cannot say what was the delay. So then someone will check it in some other data source like flight radar or other service of this type, and manually fill the values in the database. And then switching to a new data source and implementing this process of fixing the data, this improved the percentage of total created cases without enough data to make a judgment, from between 15 and 20% of cases to 8%. Sorry, this last number is not very readable. And so this is one thing you can do when the data is not perfect. You can try to fix this. You can also try to extract the information you need from the data you have. So I said that we tried to get the strike information but didn't succeed. But what we can do is we can compute statistics about disrupted flights on airports. And the idea here is that if there is a strike on the airport, or there is an extremely bad weather around the airport, not only this one flight will be disrupted, but many flights will be disrupted. And this actually correlates very well with airline rejecting the claim. If there were many disrupted flights on the, say, departure airport or on the target or the arrival airport, then the airline will usually just reject the claim for money. So this is another approach you can use to somehow get the data about, get features from history that help you. And having done all this, so we trained the model. We used LightGBM to train the model. So this is the ensemble of small decision trees, if you don't know. And we use it over XGBoost or something like logistic regression or our single big decision tree because it worked better and it was easy to use. So like things like categorical values were handled well from the start. And our model had something like 250 features. Most of them were the airport statistics. So if you wonder why there are so many features of this type, it's because you have two airports, one where you start from, the one where you land. On every of those airports, there are flights that come to the airport and flights that depart this airport, so you can count them separately. You can count various ranges of delays. So like disrupted flight is this one that is delayed more than 3 hours, but there are maybe smaller delays, maybe a lot of smaller delays, and this is also an indication of some other problem. Also, I mentioned before that if the airline is on strike, then you are not entitled to compensation. So we calculate the statistics, all those statistics that I said, excluding the airline you're traveling with. So this is used to, like, if your airline is on strike, then probably only flights by this airline will be disrupted. So if you calculate the statistics for all the other airlines, you will get that everything is fine. And we had weather features, so features extracted from the weather reports. They were less useful because there were a lot of, these reports are not very consistent between airports. So sometimes on one airport you will get some information, on another you will not. So it makes it hard to use, to actually use as a feature in the model. And the 20 features were other things like an airline. So this sort of maybe categorical features, like type of flight, is it a low-cost flight or not? And this model had the AUC score of 0.91, so the area under curve. And the ROC curve, right, this the true positive rate versus false positive rate is, you can see here. And this is the area under this curve is 0.91. So this was our classifier. And now the very important part of implementing the model in a company that has some existing process where humans do some work is explaining the model. It's telling that, it's proving that your model makes sense. And so explaining the model is very important. So the LightGBM model is nonlinear, so it's harder to interpret, but still a lot can be done. And there are many, so there are a few methods to do that. One is, like the basic one is to look at the feature importance, and there is gain and number of splits. So gain is when you calculate how much you gained in terms of the loss function when using this feature in your trees. The number of splits is how many times you used this feature as a decision point in the trees. And this gives you only global feature importance, and this is how it looks for us. I grouped up the various, so to not show you 250 features, I grouped them up by type. So there are statistics about departure airport, arrival airport, which have a very similar number of splits, weather that has a bit less, so half less, so 50% of that, maybe even less, and other which are even less important. But again, a number of splits are not very perfect. You cannot use them to explain a single observation. And there have some other theoretical faults. So there is a better way. It's SHAP values. There are sharply additive explanations introduced in the great paper, A Unified Approach to Interpreting Model Predictions by Scott Landberg and Swin Lee. So these are based on Shapley values from game theory. This can be calculated quickly for 3 models, so a type of model we have. And this can be used to explain single cases. This is something really great where you can, so the way it works is that you calculate the expected effect of this feature on the output of the model. And there is a very nice Python library called SHAP that you can use to plot, to visualize the feature importance in many different ways. And also this is recently has been added to both LightGBM and XGBoost. So you can just, when you use the predict method from these libraries, you can just get these Shapley values. And so one type of plot, a simple plot that looks a bit similar to the previous one, is the absolute SHAP values, where again I group the features. And here it looks like the departure statistics are a bit more important than the arrival airport statistics, and the weather is less important, and the other features are even less important. So it looks similar to the previous plot, but not identical. And so this is looking at this type of plots. Feature importance is very important. Feature importance is very important. Well, it lets you catch bugs. So you can see, well, you can look at this plot of all the features, and you can see that maybe there is a feature here on top that doesn't make any sense. This happened to us, like when you make a bug and something ends up used in training that shouldn't be. Maybe it contains the real answer or is broken in some other way and ends up on top in the feature importance, then you can catch it up. But also the Shapley values can be used to explain the single errors of the model. So you can look at, well, my model, so you can look at the cases you've verified with the model, and people at the company will tell you, well, this is wrong, this case is wrong, this case is wrong, and this case is wrong, why? And you can look at the individual Shapley values for each case, and then maybe realize that something is wrong with your model. Okay, so now we have the model. We have explained the model. So we are pretty sure the model is OK. Now we need to deploy the model. And the way we did that is we deployed, so we wrote a REST HTTP server. We used Bottle framework, but there are alternatives like Flask, which was deployed on the Google Cloud using Kubernetes. And this needs to be fast, or at least fast enough. So part of the job is to make sure it's fast enough. So you might need to profile the code. And when we needed to profile the code, we used cprofile and visualized the profiling with a tool called SnakeViz. And then after it's deployed, we monitor the performance, so performance in terms of speed. And here we use Prometheus and Grafana to see. And on this plot, there is the average verification time. This is a few seconds, so this seems like a lot. And it is quite slow, but this is for the needs of the company. Right now, this is good enough. A lot of this time is actually used querying some internal API. So. Okay, and then you have the model deployed, but still you need to, you cannot just trust your metrics. So let's say our AUC was 0.91, this seems good. And we measured other things like accuracy, precision recall, all this stuff. But this doesn't necessarily tell you how the model will work in production. So another thing we did was we ran the model in parallel with human verification. So the employees of GIVT would get the case, verify it, and then see what was the model's answer. And then they will, well, if the answer was the same, then everything was fine. And if the answer was different, the answer differs. So what was the reason? So what the model overlooked, basically. And then after a few iterations of this process, we ended up with a model that was agreed with the human verification 83% of the cases, and was different in 17%. And this was good enough for the current process, and this was deployed in production recently in November. And this and the current pipeline looks like this. There is automatic verification that handles cases like the delay was less than 3 hours, or the flight is outside the scope of the EU261 directive. And this handles roughly 50% of the cases, so 50% of the cases are just trivial. And then there is machine learning verification, our model, that handles 11% of all the cases, so 22% of the hard ones. And the rest falls into the hands of humans again. And there the reason why this is so high is that there is still a lot of missing data. So even when we fix the data, or when we get new providers, there are still problems with the data. Sometimes the client will say input the flight number and the airports, and they don't match. And then the model doesn't know, and then a human has to, there needs to be contact to explain what is wrong. Okay, so a takeaway message. So that for this type of project, the cleaning, merging, analyzing the data takes way more time than actually training the model. The training the model, well, we ran a few experiments, but this wasn't the main part of the job. The main part of the job was to get the data together and make sure so there are no missing values. It's unavoidable there are missing values, but you don't have absolute empty rows in the data frame or something like this. And that explaining the model, so understanding the model that you created is very important, and it can help you avoid bugs and gain trust in that your solution actually works. And there is a constant need to monitor the model. So you cannot just run one test and say, okay, this works, this is, say, covers 83% cases, agrees with human verification. Because the work changes, the law changes, the company strategy changes. So you need to check this somehow. So the way we do this, we sometimes verify the same cases with the model and human verificators and compare the results. Okay, that is all I wanted to say. Thank you very much for your attention.
Thank you, Adam. Any questions?
Thanks very much for a very good talk. You mentioned about SHAP values, and one of your slides you said you had a pie chart, and it was 83% of decisions the humans agreed with. Just for curiosity, did you, when you asked the humans what reasons they had for agreeing with the model, did you try to match that against the SHAP values, and were they very similar?
We didn't. Well, we didn't do that. So what we do now is we have a tool for the analysts that displays, so they can input the case number, identifier, and then they get, for this case, what were the SHAP values of the important features. So they can look at that. There is no, because analysts and the verifiers, they are different teams, and so there is no, this was not joined together. So the verificators that input the reasons did not see the SHAP values. The analysts that analyze this later, then they can look at the SHAP values. So
yeah, but it would be very interesting to check and see if they were the same.
Yes,
then, yeah?
So
and it's even better that they're different teams. You know,
Yes, so this we didn't do, and yeah, this is a good idea to check.
Okay, and the last question is what was your decision? Was your threshold, your classification threshold, 50%? Like your for?
So the precision was supposed to be 80%.
No, but the decision between the model, like, so it's a binary classifier, yeah, like they will get compensation or they won't. So when you had 83% agreement among the human users, did you play around with the threshold at which you classify it?
So the threshold is chosen the way that the precision on the validation set is 80%.
Okay. Okay.
So that's how I actually don't remember what is the threshold.
Okay. Thanks. Thanks very much.
Next question. Okay, no more question. Yeah.
Hello. I have a question regarding when you mentioned the hard cases. You said that 50% were automated, and the other 50% were hard cases. How hard are actually these cases? Like, how hard can they be?
Well, not very hard. So these are hard cases in that sense that delay is greater than 3 hours, or the flight is cancelled, and the flight is eligible for this compensation, and there are no obvious reasons to reject. Right. So the hard, yeah. So this means not very hard, but it's not. You cannot reject it immediately. This is so. So the way the human verificators work is they will look at the statistics of the airport too. Or they will look at the flight radar, well, if they have doubt. They will look whether there was a storm somewhere or some extreme weather event. And if they don't find anything like this, they just accept the case. There is a bit of like game theory, because you could accept all cases and just set it to the airlines. But then the airline would learn this and then reject all your cases, right? So you have to send them. You don't want to lose any good case, right? So you should be biased towards accepting, not rejecting, but you cannot send everything, right? So
And also, I saw that you have like 250 features, no, for the model, and a human verificator. How many of these features actually looking? At the end, the human is better than the ML model, no? So
yes. Human looks at way less, right? So the human verificator will look for things like whether there was a storm, right? So it will, if he or she has doubts, he will look at some portal with aviation weather and see if there was a storm or fog or ice or something like this. Or it will look at the news website looking for strike information, whether there was a strike. So kind of human. So the media, right? The available data is easier for humans to extract information from, like whether there was bad weather, or whether there was a strike, whether there was some problem with this plane earlier. Right? So it is easier for human to extract this information from the whole internet. And for the model, it's harder, so the model needs more features.
Any question? Okay, one.
Maybe a little naive question, like I don't know how quickly the users submit new proposals, let's say for claims, but can you use like historical data from the airlines already to reject or accept?
What do you mean historical data?
I mean, if you submit once blindly and then get answered, and if you get the same claim for the same flight, you just use the historical data from.
I think this is slow.
Okay.
So there is a process. Some it differs airline by airline. Some airline will have an online form. Some airline will require you to send them a letter, or required in the past. So there is this difference, and so this is just you won't get this in seconds, right? So you cannot just or even minutes, days, yeah. So. But I don't know that, right? That would be a nice trick, but maybe the airlines would, if they would realize, they would just reject everything, right? What you send them.
Okay. Is anyone question? No. Thank you.